And let me also share my screen. All right. 1 minute. Mute that. And let me minimize this. Okay. So I just want to confirm what I posted in the announcement. Um, well, I did correct the mistake I made in terms of test number 3. So the only other thing I need to confirm, of course, please note that you must submit it in a PDF format. Make sure it's done in ink. Make sure that the writing on each page is aligned as in the original document, and write your name at the top right hand of each page. And I just want to confirm, actually, the date for your final exam, which would be May 7th. I'm just looking at the official college schedule because the college actually set the dates for the final exam. So this is CHM 2045, which meets on a Tuesday. And according to the colleges, according to the college's schedule, it's 9:30 a.m. So our exam will go from 9:30 to 11:30 exam, all right? And it's in the same room as always, room 107. And it will be comprehensive. And I'm going to try to make it a question per chapter, right? So each chapter will have a question in it, all right? So I just thought I should, confirm that so that we're all on the same page. So, questions
So
about this? Oh, I'm sorry.
It's on Tuesday?
Let me see what Thursday, May 7th. And the reason why, and I think you're raising the question because normally it would be on the same day as the class, the class period. What happened is that I have, hold on, let me see here. Yeah, actually, that's what it says here. So Thursday, yeah. What happens is that I have you guys and I have another class immediately after. If I were to have this class on a Tuesday, then it would run into the time for the final exam for the other class I have, which is the introductory chemistry class. So I think that's the reason why it is done that way. So the introductory chemistry class, their exam is on Tuesday at 11 o'clock. And for your exam, it will be on Thursday at 9:30. If it was on Tuesday, the exam would finish at 11:30, which runs into the introductory chemistry class. And that's the reason why that is. All right?
Thank you.
Okay. Somebody's saying something in the chat. Okay, so the problem with the testing center, and this is a question that is being asked by Miss Betancourt, is that students keep telling me that there's no more slots, right? So based on that, I've decided that, okay, you know what? Let's forget the testing center for the rest of the semester. And I decided to do it this way, where the test number 3 is a take home and the final will be done in class or in the classroom. Now, if you're not able to come for whatever reason to the scheduled time in class or in the classroom, please let me know and then we can make an arrangement. You can come to me during my office hours and you can do it there. All right. But that's the best we can do right now because everybody keep telling me that they can't get a slot to do any test for the rest of the semester. So that's basically how things have worked out. Okay. Any other questions concerning? Oh, there's another comment. Let me see here. I need to take that final exam before that. Oh, okay. So this is who now? This is, Miss Lush. Okay. Well, like I said, we can make arrangements. You're leaving on the 6th. So we can communicate afterwards to find out exactly when would be a mutually convenient time for us to make that arrangement. All right. So We can talk after. All right? Okay, let's see. Somebody else is saying something. Okay, so I'm not taking any attendance per se because Zoom automatically records your presence. All right? So that's the answer to Miss DeGraw's question. Okay, any other questions before I move on? Any other questions? Any other questions? Okay, so let's talk about, I think there's one more question that needed to be done in, let me see here. In the assignment, I forgot what assignment number it is.
10.
Assignment 10. Yeah, that sounds about right. I just had it here. Where is it? Okay, I hate when this happens. Okay, I'll have to bring it back up. So let me go here, 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 files. And it's assignment 10. Okay, so as I recall, the only thing that's remaining in this assignment is this question right here. It says draw appropriate MO diagrams for the atomic molecules Si2 and O2 minus, and for each determine the bond order and whether the molecule is paramagnetic or diamagnetic. Okay, so just to quickly review, because this would have been covered in the videos, this is based on what is called the molecular orbital theory, all right? So basically, the molecular orbital is basically the result of atomic orbitals overlapping. And basically, as stated here, molecular orbitals are to molecules as the blank here, which would mean atomic orbitals are to atoms, all right? And basically, according to the molecular orbital theory, the molecular orbitals are formed as a result of the combination of atomic orbitals. Now, how do they actually combine? Basically, what will happen is that whenever you have two atomic orbitals combining, the result will be two molecular orbitals. In fact, I remember when I was a student, I remember my instructor saying that, orbitals cannot be, what did he say? Orbitals cannot be created nor destroyed, right? So what that means basically is that if you have two atomic orbitals coming together and combining, you're going to end up with two molecular orbitals, right? So basically, when that happens, the molecular orbitals form, the two of them, one will be of a lower energy compared to the atomic orbitals from which they're formed, and the other one will be a higher energy, right? So as stated here, one of the orbitals, which would be of a lower energy, one of the molecular orbitals, which would be a lower energy, is called a bonding molecular orbital. Its energy will be lower compared to the separate atomic orbitals, and therefore when electrons go into that orbital, it increases the stability of the molecule, all right? On the other hand, the second orbital that is formed is called an anti-bonding orbital, and its energy will be higher compared to the atomic orbitals from which they're formed. And as a result, when electrons goes into those orbitals, that will result in a decrease in the stability of the molecule, all right? So just to give you a simple example, in fact, the simplest example I can come up with is where you have two 1s orbitals. So we're looking at the hydrogen atom here. There's only one electron in each hydrogen atom, and the electron will go into a 1s orbital, right? So when the two hydrogen atoms come together, they will basically combine to form two molecular orbitals. One would be the bonding molecular orbital, which would be lower in energy compared to the atomic orbitals from which they're formed. And the other one would be the anti-bonding molecular orbital, which will be of a higher energy compared to, again, the orbitals from which they're formed, right? So these two electrons now, the question now becomes, where will these two electrons go in the case of the molecular orbitals that are formed? And the answer is the two electrons will go right into the molecular orbital, which would be the bonding molecular orbital down here, all right? So therefore, this would represent the electronic configuration of the hydrogen molecule. And another thing I should mention here is that if you remember in the previous chapter, we said that each atomic orbital can have no more than 2 electrons. Well, the same is true for molecular orbitals. Molecular orbitals cannot have more than 2 electrons in them. So basically, these 2 electrons will go into the molecular orbital here, which is the bonding molecular orbital. And if you were to add another electron, then that electron will go into the antibonding molecular orbital. Now, the bonding orbitals and the molecular, well, the bonding and anti-molecular orbitals have some special designations associated with them, right? So, of course, we're familiar with the fact that, okay, over here we have the 1s orbital. Well, this orbital here, which is a bonding molecular orbital formed as a result of the combination of these two, is called a sigma orbital, and more specifically, sigma 1s, right? Sigma 1s meaning that the molecular orbital is formed from the 1s orbitals, all right? And then this orbital here, which is the anti-bonding molecular orbital, we call that the sigma star 1s orbital, right? The star here indicates that the orbital here is anti-bonding, all right? So that's what happens in the case of two hydrogen atoms coming together. Now, what if it were two helium atoms coming together? Now, helium would have 2 electrons in each 1s orbital. So I'm drawing those orbitals like so. Whoops. All right. So the question now becomes, where will the electrons go? Well, the first 2 will go here in the bonding molecular orbital, and then the next 2 would go here in the anti-bonding molecular orbital. All right. And what's going to happen is that the bonding effect that exists because these 2 electrons here are in the bonding molecular orbital will be offset by the anti-bonding effects due to the 2 electrons in the anti-bonding orbital. So the result would be that basically no bond will be formed. There will be no bond that will be formed in the case of the helium-2 molecule. So that's why helium does not combine with another helium atom to form a diatomic molecule. Basically, helium exists in nature as a monatomic structure or a species, all right? Okay, so this is a relatively simple example, but what if we get to something more complicated? Let me see if I can bring that up in the next slide. Well, before we get to the more complex situation, what this slide is showing you here is, or are the possibilities when it comes to the p orbitals. Now, if you recall, we said in the previous chapter that the p orbitals exist at mutual right angles and they appear in sets of 3s within the same subshell, right? So here we have the 2 p orbitals, px, pz, and py. Now, when they come together, what will happen is that the 2p orbitals from different atoms will overlap like this to form what we call the sigma 2p bonding orbital and the sigma star 2p, which would be the anti-bonding orbital. So this is an end-to-end overlap between these 2p orbitals, resulting in these this arrangement, all right, this combination. Now, in the case of the other p orbitals, the pz and the py's, they will be parallel to each other. So they will overlap sideways like this, and they're going to form what are called pi bonds, right? And you have 2 different types of pi bonding. You have the pi, or pi molecular orbitals, I should say. You have the pi bonding molecular orbitals, which is this right here, and then you have the pi anti-bonding molecular orbitals, right? So the pi orbitals, bonding and molecular and anti-bonding, which are formed from the parallel 2p orbitals. And we have a similar situation when it comes to the 2py orbitals. Again, you're going to have the bonding pi orbitals and the anti-bonding pi orbitals. So basically, as it pertains to the p subshell, when it comes to the type of bonding that will take place, basically you're going to have the formation of bonding and anti-bonding sigma bonds, and then you, if necessary, you're going to have antibonding and pi bonding, antibonding and bonding pi orbitals, and both of them, two of them, here and here, all right? You're going to see how all of this come together when it comes to the molecular orbitals of more complex molecules. So this is showing you basically for period 2, the type of molecular bonding situation and the type of molecular orbitals that will be formed when we have atoms that are linked together to form diatomic molecules, right? So basically, what you're looking at here, I'm going to start off with lithium here, right? So in the case of lithium, you're going to have, firstly, these orbitals here, which would be the orbitals formed as a result of the overlap or the combination of 2s orbitals. You're going to have the sigma bonding and sigma anti-bonding formed from the 2s orbital. And then up here, we have the pi bonding orbitals and the pi anti-bonding orbitals formed from the 2p orbitals. And then we have the sigma 2p bonding and the sigma 2p anti-bonding orbitals, again, formed from the other 2p orbitals, right? So this would be basically the arrangement of the molecular orbitals in the case of lithium, and the same arrangement occurs in the case of beryllium, and the same arrangement occurs in the case of boron and carbon and nitrogen. But something happens when you get to oxygen. When you get to oxygen, what happens is that this arrangement here, where you have the sigma 2p having a higher energy compared to the pi 2p's, it's flipped. The pi 2p's will have a higher energy compared to the sigma 2p's. And then that trend continues for the rest of the atoms or molecules pertaining to period 2. So this arrangement here in terms of the energy of the molecular orbitals will be the same as in the case of fluorine, and will be the situation in the case of neon. Okay, with that said, once you establish the orders of the molecular orbitals, it's all a matter of assigning the electrons, all right? So in the case of lithium, and by the way, this pertains to the valence shell. I should stress that. This pertains to the valence shell, right? So the inner core electrons will not be involved in what we're discussing here, right? Because the inner core electrons are not involved in bonding. Bonding only involves the valence electrons. Okay, so with that said, in the case of lithium, lithium has only one electron in the valence shell for the atom, but there are two of them. So therefore, both electrons will go into the lowest molecular orbital, which would be the sigma 2s, right? To get from lithium to beryllium, you need to have two more electrons, and therefore those two electrons will go into the anti-bonding molecular orbital sigma 2s, all right? And then now, to get from beryllium to boron, you need to have two more electrons. Where will those electrons go? Those electrons will all go into the pi 2p orbitals that you see here, right? So that's what we end up with right here. And then to go from boron to carbon, you add two more electrons that would result in the electrons pairing up in the pi 2p molecular orbitals. And then the next two electrons going from carbon to nitrogen will go into this orbital, which will result in this electron configuration. And then you just continue until you get to neon, where basically all the molecular orbitals would be completely filled, right? So that's basically how you would determine the molecular orbitals or how the electrons are distributed among the molecular orbitals, all right? So that's basically how this is done. All right, so let me talk about another term. Oh, somebody's saying something in the chat. Oh, yes, I am recording. Thank you for asking. Yes, I made sure that I turned on the live stream. All right. Some terms I need to introduce to you here now. So I kind of introduced it to you earlier, but without really stating it explicitly. This term is called the bond order. It's a measure of the multiplicity of the bond. It's very simple, actually. Basically, the bond order refers to whether or not a bond is a single bond, double bond, etc. So if the bond order is 2 between two atoms, that means that there's a double bond between them, right? Now, in terms of the molecular orbital diagram that I just showed you, how do we calculate the bond order? Well, there's a formula here which shows you how to do that. Basically, all you do is count up the number of electrons in the bonding orbitals and then subtract from that the number of electrons in the anti-bonding orbitals and then divide by 2. And that will give you the bond order for the particular structure. All right. So let me go back to this diagram here. So for example, in this case, if I were to calculate the bond order for the lithium molecule, it would be 2. So let me write here, BO is equal to 2, which is the number of bonding electrons in the bonding molecular orbital, minus 0, because there are no anti-bonding electrons, divided by 2, so that's equal to 1, right? So what that means is that in the lithium molecule, there is a single bond. Let me draw a line here and here to separate them. And then here, in the case of beryllium, the bond order would be equal to 2, which would be these bonding electrons, minus 2, which would be these anti-bonding electrons, and then divide that by 2, and that will be equal to 0. All right? So that's basically that. And you can do the calculations for the others. In fact, let me do the calculation for this one here. In the case of boron, right? The number of bonding electrons, to calculate the bond order, the number of bonding electrons would be 2 plus 2, which would be 4, minus the number of anti-bonding electrons, which would be 2, and then we divide that by 2, and that would be equal to what? 1, all right? And so on and so forth. So that's basically how you would determine the bond order for any diatomic molecule, all right? Okay, any questions about this? Any questions? Okay, so okay, so let's look at this question. It says, when an electron is removed from a nitrogen molecule forming the N2 plus ion, the bond between the N atoms are weakened. And then it says, when an oxygen molecule is ionized to form O2 plus, the bond between the oxygen atoms is strengthened, right? So the question is asking for you to explain this difference. All right, so it basically comes down to the bond order in each case. So let me go back to this diagram right here, and let me erase all this here, because we'll be focusing on N2 plus. So let me write down here, just to remind me, N2 plus and O2 plus, all right? Now, in the case of N2 plus, to get from N2 to N2 plus, we're going to remove this electron right here, all right? So let's calculate the bond order in the case of N2 plus. So, how am I going to do this? Okay, so let me say for N2 plus, the bond order would be equal to, okay, so remember now, we have removed this electron here, right? So we need to count up the number of bonding electrons. So that would be 2 plus these 4, so that's 6. So 6 minus, and then the number of anti-bonding electrons would be 2 plus 1, 3, right? So we divide that by 2. So that would be what? 6 minus 3, that's 3. Divide by 2, so that's 1.5. All right? So we're going to do the same thing now in the case of O2 plus. Now in the case of O2 plus, we're going to remove one of these two, right? So the bond order in the case of O2 plus would be equal to, we have to hand out the bonding electrons first, 2, 4, 6, 8. So 8 minus 2 and 1, 3. divided by 2. So that's 8 minus 3. That's 5 over 2, which will be 2.5, right? So basically, the bonding in the case of O2 plus will be stronger because the bond order is 2.5 as opposed to N2 plus where the bond order is 1.5. So that's basically the explanation as to why the O2 plus would be of a stronger, let me see how the question words it. Right, it says that the bond is weakened between the N2 atoms in the case of N2 plus, but stronger in the case of the O2 plus molecule or ion. So that explains why. The bond order basically what it comes down to. O2 plus has a higher bond order compared to N2 plus. Okay, somebody's asking a question here. Why do we remove one of the arrows? Because the question is asking for the situation for N2 plus, not N2, right? So therefore, to get from N2 to N2 plus, we have to remove the electron from the highest molecular orbital here, right? And the same is true in the case of O2 plus. We have to remove an electron from the highest molecular orbital in the case of the O2 molecule. So that's the reason why we remove the electron, all right? Okay, let me see here. Is there anything else I need to say? Okay, tell you what, let me go. I may come back to this later on, but I want us to do the question that remains in assignment 10. So let me go here. Okay, so the question says in assignment 10, question number 2, it says draw, let me make this smaller because I'm going to need the space to draw the diagram. Okay, so the question says, draw appropriate MO diagrams for the diatomic molecules of silicon 2, Si2, and O2 minus. All right. So let's see here. For each, determine the bond order and whether the molecule is paramagnetic or diamagnetic. All right. So in the case of Si2, what I'm going to do is I'm going to start off with, now in the case of silicon, the valence shell is the third shell, right? So basically we'll be concerned with only the orbitals in the third shell, which would be 3s, and there's only one of them. And then you have 3 3p's. All right. And I'm going to do the same thing on this side. Right. So the 3s here and the 3 3p's here, right? So in the case of the 3s, they'll come together to form a 3s, a sigma antibonding formed from the 3s orbital and 3s bonding down here. All right, I'm just going to draw the line so that you can see the associations. All right, so basically these molecular orbitals are formed as a result of the combination of these 3s orbital. I hope I have enough space here. Now, in the case of the 3p orbitals, they will combine to form sigma, not sigma, I'm sorry, pi, three p and pi 3p here. And then you're going to have the sigma 3p here, right? And then these will be bonding, of course. And then up here, we're going to have the anti-bonding. So you're going to have, why do I keep, oh, okay. So I'm going to have pi anti-bonding 3p, pi anti-bonding 3p. And then unfortunately, I have to just do this here. This will be sigma anti-bonding 3p, all right? So just to show you the associations in this case, You know what? Let me take this out. Let me just do it on a separate document because it's looking untidy there. All right, so let me use this instead. All right. So let me start off with three S, and then sigma 3S, and then sigma antibonding 3S. So these will be the associations here. And then now we get to the 3p orbitals. And down here, we're going to have the 2 pi 3p's. And then here we're going to have the sigma 3p's. And then up here, we're going to have the pi antibonding 3p's. And then 2 of them. And then here we're going to have the sigma antibonding 3p's. All right. And again, let me just show how they're formed. Like that. Okay, so basically, the next thing we have to do is look at the number of valence electrons in each atom. Now, silicon is in group 4, so therefore the first 2 electrons will go here, and then 1 electron will go here, 1 electron will go here. And by the way, these would be the 3p orbitals. I forgot to label those. So this arrangement would be the same as on this side. So you're going to have these 2 electrons here, and then you're going to have those electrons going there and there, all right? So the question now becomes, how do the electrons distribute within the molecular orbitals that are provided in the middle? So here we have 2 electrons here, 2 electrons here. So basically within the sigma level here, you're going to have 4 electrons. The first 2 would go here, and then the next 2 would go here. And then now, for the 4 electrons that results from these electrons in the 3p sublevels, the first 2 would go here, and then the next 2 would go here and here. And that would be it, all right, in terms of the electron distribution among the molecular orbitals. So that answers the first part of the question. Now, the next part is asking for the bond order. Okay, so to get the bond order, the bond order, if you remember I said, is the number, let me do it here. Bond order would be equal to the number of bonding electrons. So the bonding electrons would be 2 plus 2 plus 2. So that's basically 6 minus the number of non-bonding electrons, which would be, I'm not non-bonding, I'm sorry, keep saying non-bonding. Anti-bonding electron, which would be 2 right here. All right, and then divide that by 2. So 6 minus 2 gives you 4 over 2, which would be equal to 2. So therefore, the bond order is 2, which means that in the case of the Si2 molecule, it's a double bond. All right, so that basically answers that. Now, let me see if there's anything else I need to answer. Oh, and whether or not the molecule is paramagnetic or diamagnetic. Now, this goes back to something that we learned, I forgot which chapter it was, right? If you remember, we said that a molecule is paramagnetic if it has unpaired electrons, right? And in fact, we refer to atoms, but it's also true for molecules in this case, right? So basically, if any unpaired electrons exist, that would make the structure paramagnetic. If there are no unpaired electrons, if you have all the electrons paired up, then basically that structure would be diamagnetic. So if we go back to this diagram right here, you'll see that all the electrons are paired up within the same molecular orbitals in each case, right? So therefore, this molecule is diamagnetic. Diamagnetic, all right? So that's basically how we answer that. And I think we basically answered all the questions in relation to, let me just check here, in relation to SI2, all right? And that's basically it, as far as that is concerned. And if you understand that, then you should be able to do the same thing for O2 minus, all right? So I'm going to leave that for you to try on your own. If you have any questions about that, please feel free to contact me. But basically, in the case of O2 minus, you actually will be using, let me show you. You'll be using this right here. Hold on 1 minute. Oh, shoot, I can't erase this. Hold on. I should be able to get rid of this. Okay. All right. Basically, in the case of O2 minus, you'll be using this molecular orbital configuration right here, right? The only difference is that you're adding an electron to get it from O2 to O2 minus, which means that the electron will be added here, right? So in fact, let's look at this. That would be the electron configuration of O2 minus. So what do you think the bond order is? How would you calculate the bond order in this case? Anybody? Well, let me ask you this first. What's the total number of bonding electrons? Well, what's the total number of bonding electrons? What's the total number of electrons occupying bonding molecular orbitals? The bonding molecular orbitals are the ones without the stars. No idea? Okay, let's see. Somebody's saying two persons, actually. Let's see what you guys... Okay, somebody says 4, and another person says 8. One of you is right. Anybody want to take a guess as to which one? Okay, let me see here. Okay, there are 4 pairs, you're right. But what I asked for is the actual number of bonding electrons. So it's actually 8. All right? So the number of bonding electrons here, let me do this. So the actual number of bonding electrons here, whoops, hold on, is 8. And what would be the number of anti-bonding electrons? Now, those will be occupying the orbitals which has a star associated with them. Okay, let's see what this person says. 6, let's see here. 2, 4, and 1 here. So actually it's not 6, it's 5. All right? You have 2 here, you have 2 here, and 1 here, right? So basically, you're going to have 8 minus 5, oops. 8 minus 5 divided by 2. So that's 3 over 2, which would be equal to 1.5. All right? So that would be the bond order for the oxygen. Now, the next question is whether or not this structure would be diamagnetic or paramagnetic. So which one do you think it is? Remember, diamagnetic means that all the electrons are paired up. Paramagnetic means that there's at least one unpaired electron present in the structure. So in this case, would it be diamagnetic or paramagnetic? Well, nope. Okay, somebody says paramagnetic. And why do you say that? Who is this? Oh, Miss Betancourt. Why do you say it's paramagnetic? Yeah, because there's one electron that is not paired up, and that would be this electron right here. Hold on. This electron right here is unpaired. So therefore, the resulting structure would be paramagnetic. All right. So that's basically that assignment. So what I'm going to do now, I am going to create a Dropbox for this one. Okay, so today is the 28th. So I'm going to okay, I'm going to let this be due on Friday. Okay, so that's pretty much it. I was thinking of discussing hybridization, but I'm going to leave that alone. But I would strongly recommend, especially for those of you who have to do organic chemistry, right? I would strongly recommend that you read at least and try to understand the whole topic of hybridization. I think I covered it in the videos, but it's also in the PowerPoints, in the earlier parts of the PowerPoints, right? So I'm talking about starting from, well, we talked about molecular shapes already. So after that, hybridization, sp3, sp2, and so on. So, and then they talk about the bonding in certain organic molecules like butene and so on. So I would strongly recommend that you read upon that at least. For those of you who have to do organic chemistry, especially. All right. So that's pretty much it, folks, for the semester. Unless you have any questions you want to ask concerning, well, I guess pretty much anything by now. If you have any questions about the test, about the take-home test or the finals or anything, the only thing I cannot give you are the answers to the final exam questions. At least not before the final itself.
So for the finals, I I have to take that at that date and time. No other
No,
options.
right. So as I was saying, I don't remember who was it who somebody was saying that they can't make it to that date. If we can make an arrangement for you to do it at some other time, I have no problem with that. You'd have to come by my office though. All
Okay.
right. So if for some reason you're not able to make it to that specified time, and again, let me remind you that time is, well, the day is May 7th, 9:30 to 11:30. All right. If you can't make it then we need to make an arrangement. Somebody's asking something in the chat. Does it have to, hold on. Yes, you mean, I'm talking about the final. The final has to be in person, so you have to come. Oh, you're the person who said that you can't make it, right? Yes, so you'd have to come to me in person, come by my office to do the test if you cannot come to the scheduled time. All right, okay. Oh, by the way, before I forget, is what's his name here? Hold on. Is oh, Khalil. Unfortunately, for the same reasons why I'm not on campus right now, I cannot meet you later on this evening. Um, so I'm thinking that Thursday, about the same time, is the next best time for us to meet. All right. So let me know if you can make it on Thursday. All right. Yeah. Okay. Any other questions? Any other questions? No questions? No questions? Sure? Okay, so if there are no other questions, that's pretty much all I have for you today. I'll be available for office hours, the usual office hours, which for the rest of this week would be Wednesday. I'll be at the Ocala campus from 2 to 5. And tomorrow, I'll be at the Citrus campus from 1 to 4. And on Friday, I'll be at the Ocala campus again from 2 to 5. All right. Okay, so if there are no other questions, that's it for me today. And I guess I won't see you until your final exam next week, Thursday. All right. All right. So take care. I'm signing off.